for coming by this week's iteration of the NPA. So it's actually my absolute pleasure to introduce Jamie Karthein. She's currently a theoretical nuclear physicist at the Center for Theoretical Physics at MIT. She received a PhD from the University of Houston in 2021 under the supervision of Professor Yale Wright, and was awarded the Danny Wells Outstanding Dissertation Award for her work on the QCD collision state, as well as net charge fluctuation. As of January of 2022, Jamie began her tenure as an NSF Ascending Postdoctoral Fellow at MIT, focusing on thermodynamic studies of strongly interacting matter by mapping out the QCD phase diagram. And of course, she's particularly interested in the search for a critical point in the diagram and the characterization of the transition between ordinary matter and the quark-gluon plasma. So without further ado, Jamie, take it away.
Thanks so much for the introduction, Fernando, and for the invitation. I think it's a really unique opportunity to come to the NPA seminar and get to talk with experimentalists and learn about a lot of new things. I have on my schedule a lot of jet discussions, and I'm not a jet person, so I'm really looking forward to learning a lot and enjoying the discussions, and very happy to be here. So let's get started. I will be talking today about the fluctuations of conserved charges and what we can learn about the structure of QC matter, of strongly interacting matter, by utilizing those fluctuations. So start from something familiar, the ground truth, QC phase diagram. There are a lot of things on here which are not yet confirmed, right? The reason I chose this one to show here is because I like how you get to see all the different experiments covering the different energies throughout the different baryon densities or baryon chemical potentials here on the x-axis. But all of these questions here, whether there's critical point, where does the transition line go at high density, what are the phases of high density, what are the degrees of freedom in the vicinity of the transition, these are all questions that drive me toward the study of the QC phase diagram. But if we look at what we really know from ground truth, from Lattice QCD, what we know is basically where the transition line goes at very small values of the baryon chemical potential. So these results are the continuum extrapolated results from the Budapest collaboration. And what's shown in the kind of secondary plot here is how that transition line compares to different freeze-off parameters from different experiments, different experimental data, and how you fit the freeze-out curves. So if we want to go beyond just what we know from first principles, we can also add some models to the phase diagram and try to fill out kind of this conjectured phase structure that I was showing on the first slide. So for example, this is a plot from Veronica Dexheimer. So she uses the chiral mean field model, which has in it a critical point, and they can actually describe this critical feature and get this nice first order phase transition line and be able to connect to this very high density realm for where neutron stars live, where neutron star mergers live. And one final phase diagram that is also really interesting to show. This one is from the recent white paper that we had for the long range plan. And what I like about this one in particular is that you can also see now compared to a bunch of different experimental results, again with some freeze-out parameters, also the dielectron points showing the different temperatures that are probed in the experiments, and again some nice constraints from the neutron star community with these relativistic simulations of these neutron star mergers and binary neutron star mergers, filling out again this high density part. And again, this is the first principles ground truth Lattice QCD transition line kind of carved out at the low density phase, and in the very low chemical potential area, these are the freeze out points for the 5 highest beam energies for the beam energy scanning program. And you can see that if you have different, let's say, degrees of freedom, if we take the different flavor states, then we can actually kind of fill out this band. And Fernando did some work showing that this nicely kind of fills out the two, let's say, outer bars of this phase diagram transition line with these light states and the strange states. But there's a big gap in the middle here, if we're talking about how much experimental data is actually available to us. And this gaping hole is something that, has been undertaken, and thankfully the data is coming soon. The run of the Vinci Scan 2 has already completed last summer, and it's going to be a lot more coverage of the phase diagram with the fixed target going all the way out to 750 or so MEV in UV. So we can get to pretty large chemical potentials with that new program and the new data that's going to come out within the next 1 to 2 years, something like that. I think we'll see what we hear about a cork matter in. We're just talking about that 10 months or so, some preliminary stuff maybe. So in this QCD phase diagram, whenever the beam energy is going very low, so we have this transition line and this conjecture critical point here. But what you see here is the transition curve going out to the very high density, and I'm also showing the different freeze-out curves. So the freeze-out curves for kinetic and chemical freeze-out, I'm going to quickly define those freeze-out phases in just a moment. So in order for us to actually locate or be able to say what observables are going to tell us about the signature of this critical point, the theory community needs to say, what they should look for. And, spoiler alert, it's going to be higher order moments. And that's what, the experimentalists have been trying so hard to get some nice error bars so we can actually see whenever we have these higher order moments, for example, of net proton, if we can see some sort of signature in a large signal peak or some evidence of a dip in the net proton spectrum as a function of the beam energy. So this is the canonical thought, right, about the evolution of a heavy ion collision. And here we can look at the different phases, but what I really wanted to emphasize is the chemical freeze-out phase, because that's going to be a lot of where we are going to be talking about in this plot, and where we're actually going to probe with these fluctuations. So the chemical freeze-out is a stage of inelastic collision. So we don't have any more changing the particle type. So this is when the chemical composition of the chemical freeze-out is going to be fixed. You have your yields and your fluctuations from this moment are reflected in the experimental data. And for the kinetic freeze-out, that's when particles are so sparse that they can no longer collide elastically. They don't exchange any sort of energy, any sort of momentum. So this is when the different spectra correlations are fixed. So from the experimental perspective, we can get access to the fluctuations by looking at different distributions. So here I'm showing for the star beam energy scan, different energies from 200 to 707 GeV, and what the particle distribution looks like as a function of the net proton number. And from these distributions, you can find the moments or the cumulants. And this one in particular, the higher order one, is what has been of so much interest in these recent years, and particularly trying to nail down these error bars to see if there's a signal critical point somewhere in here. Yeah, so these are the different order of the moments in the distribution. So C1 would be the mean, C2 would be the variance, C3 is skewness, and C4 kurtosis. So essentially, if you want to take higher order moments of this distribution, then you need more and more statistics, basically. So the mean you're going to know very well. You know essentially how many particles you have. And then the variance is something that's also relatively, something possible to estimate. And as you go higher in the distribution, it's more statistics hungry for you to get those higher order moments. So C5 and C6 will also be plagued by larger error bars. Yeah, so you can see that the statistical uncertainty, for example, here in this point with the largest error bars, is the main driver of the uncertainty. There's some systematic as well that's being driven down, but that's why I could just put that for a moment. You're breaking down this this plot here, so the number of events in, this region is very many, right? So we can get enough statistics in order to say, okay, here's what we're going to have in terms of our error bars in that region. Yeah, sure. By the way, I'm very happy to take questions, so please stop me if anything is not clear. Great. Let me just go back. Sorry for hopping around. Yeah, okay. So from the experimental side, we have the cumulants, the moments of the distribution, and from the perspective of trying to understand chemical freeze out, those fluctuations, those moments tell us a lot about how we can extract these chemical freeze out parameters. So for example, how we get the coordinates, if you will, in the phase diagram T and UV for these different beam energies. And if you take, the particle yields, then you don't know what the volume of the system is going to be at the time of freeze out. So if you take some ratios, then you can eliminate that at least naive volume dependence. To leading order, you can eliminate the volume dependence by taking these ratios. And again, when you take the fluctuations, you can use them as another tool for extracting these freeze out parameters, these coordinates in the QCD phase diagram. Now, from the theory side, we can calculate the fluctuations. We can calculate these moments as well. And those are going to be basically derivatives of the pressure with respect to the different conserved charge chemical potentials. And that gives us different moments of distribution. So, for example, we have one derivative, pi 1 is going to be the mean, pi 2 the variance, so on and so forth. And again, the power of taking these ratios of different moments also gives us the ability to do a naive comparison between experiment and theory, because we have access to the same quantities, where in the experiment you have, for example, the variance over the mean, we can calculate pi 2 over pi 1. Now there's some caveats there. You need to be able to have the same experimental cuts as the system and all of these different caveats that one should keep in mind when comparing experiment to theory. But this provides a very powerful tool because we're probing really that moment of lasting loss of condition with the chemical freeze out here by studying the fluctuations. So from the theory side, there's a lot of data on these susceptibilities from first principles as QCD. So for example, if we look at quark susceptibilities, so the up quark and the strange quark, we can take their second susceptibility basically, so pi 2 U and pi 2s for quite a large range of temperature for Lattice QCD calculations. There's many off-diagonal fluctuations as well, many off-diagonal susceptibilities that are available from, for example, here, this is the results from the Budapest collaboration, and also ratios of these higher order moments. So this one that we're particularly interested in, looking at the fluctuations of net baryon number, and this is something that is going to be discussed quite heavily in this talk. So this is the second order moment of the net baryon fluctuations, and we'll see how we can describe that within our models. Okay, so in this talk, I have my main motivation to highlight how you can get access to rich features of the QCD phase diagram by utilizing the fluctuations, calculating the fluctuations. And first, I will tell you about the model that I'm mainly going to be using, which is the Hadron Resonance Gas model, how that compares to the ground truth first principles as QCD results, and then study that particular model and see how we can describe as much of that first principles data as possible. And then in the next section, I'll tell you about how to look at the fluctuations as correlators between different conserved charges. This one I talked about at Hotworks. So if you're at Hotworks, you'll remember a little bit about that. And finally, I want to tell you about how we can actually estimate the higher order susceptibilities and the effect of the QCD critical volume phase. Okay, so let's jump right in. So the Hadron Resonance Gas model can be described basically in this way. So it's given by the pressure, which we can take as the derivative of the log of coefficient function. And it's a nice simple model that in principle has no free parameters, except for how many states you want to include in your gas, right? So how many hadronic resonances you include in your gas. So we have this grand canonical picture, which is the one going to be worked with. We can talk about these fluctuations in this way. And this freedom in the choice of the particles, we're going to study by utilizing lists of particles coming from the particle data group and see how we can best describe the hadronic spectrum. So now comparing this model that we're going to use to Lattice QCD. So it's been able to describe very well, and the reason for its popularity is the fact that it can describe very well many different absorbances or many different quantities that are captured in it for Lattice QCD. So for example, the equation of state I'm showing here on the left. So for the pressure, energy density, and entropy density, you can see the solid curves are the Hadron Resonance Gas model predictions, model calculations, compared to the Lattice QCD data in the nice continuum extrapolated bands, and they agree very well up to some temperature to which the system shouldn't be treated as a gas hadrons anymore. We've had deconfinement, so we can treat this deviation as indication that there's a change in the degree of freedom in the system.
How many terms do you keep in the sum of a hadron?
Yeah, so it depends on the particle list, which I'm going to show in just a minute. So essentially, it can range from something like 600, 500. Again, going from the list from the PDG to something like 1500 if you're using the core model. So yeah, I'll show that in just a minute. Thanks. So let me go back and make sure I understand your question. So this sum here.
Yeah.
Yeah, so this is the sum over all the states.
Right.
Yeah, so this sum over all the states is the freedom I have as a choice.
Yeah.
And so I'll introduce the different lists that I'll use in, I think, the next slide.
And so what justifies ignoring the interactions? Is it a large N kind of thing? Is that the motivation?
So,
Or large number of colors?
so right, so exactly. This is an ideal HRG gas, which means that there are no interactions. It's a non-interacting gas that interacts essentially through having higher order resonances. So in principle, you have the mesons and the baryons interacting via having these higher mass resonances that you wouldn't have in the ground state. But you don't have, for example, repulsion, right? You don't have a hardcore radius, but I'm going to go into a section of this talk which is exactly gonna hit that.
Yeah.
So the ideal HRG, the reason people use it just to first order is because it matches Lattice QCD so well.
No, sure. I just want to understand.
Yeah, so we're going to go into that in detail. Let me just finish describing the list, and then the talk is actually no problem at all. Yeah, so going back to the question about how many terms do we actually have in this sum? Again, that's about how many states we're going to use, and what we're going to look at in my talk today is several different lists. One which is just kind of the vanilla PDG, I would say, so only the very well-known states from the experiment. So the PDG gives a ranking of the different particles between 1 and 4 stars. The ones which are very well known are the 3 and 4 star states, and the 1 and 2 star states not so much. So this version of the PDG in 2016, there were 608 states that were very well known. Now, if we expand that, that's what we call the PDG 2016 plus list to include the 1 and 2 star states as well, then we have more states. And these are specifically mostly coming from the strange sector. So you're adding more in the strange sector. And again, going to kind of a limiting scenario, we're using the quark model that can predict all the different types of particles possible with the different combinations of quantum numbers. Then this is, again, kind of a limiting case of the maximum possible number of states. So the plot I'm showing here on the right is just comparing each of these lists. And what you can see is, indeed, if I look in the strange sector, you have going from 2016 to 2016 plus a few more states in the Lambda and Cascade section. But in quark model, many more states, many more than could be hoped to measure, that could be hoped to be measured experimentally. Okay, so let's get into what you can do to modify the Hadron Resonance Gas model. So I showed this before, which was the ratio of fourth to second order susceptibility of the net baryton number as calculated on the lattice. And again, I'm showing the comparison to the HRG model curve here. In the HRG model, all even ordered derivatives are the same. So when you take the ratio is 1. So when you have something like this, which is a very interesting probe of the critical features of the QCD phase diagram, the HRG model fails. We don't have a good agreement with the last QCD data. If we look at different sectors, different flavor sectors, we can also have a look at this fork susceptibility, which is a mixed fork susceptibility of up and strange. And you have the lattice data here in blue as compared to, let's say, the vanilla PDG in 2012 and the fork model list. And not really does it justice. The shape looks pretty good here for the fork model, but it overestimates. And this is not giving us the right kind of shape. And maybe we can do better. So what can we do? How can we change the HRG model to actually add some sort of interactions to try to get a better description of as many of these quantities from the lattice as possible? So in this improved description of the higher order cumulants, we're going to add a repulsive interaction. So this is actually a minimalist extension where we just add repulsion between baryons with baryons, so you can have overlapping baryons and antibaryons with antibaryons. So this is adding a hardcore radius, which we can constrain with very nice ratios, which are going to be sensitive to just the hardcore radius, so just the additional parameter that we've added to the model. And we can also constrain the hadronic spectrum. So which one of the lists that I introduced before is the right one with another set of quantities. We'll be able to walk away saying, okay, how many states should I need? And what's the most likely size of this hardcore radius that I've introduced? So this excluded volume HRD model is the one that I'm going to be using. And as I said, it has interactions between baryons with baryons and antibaryons with antibaryons.
Sorry, let me ask you, how would you account for the widths of these like super high resonances?
Yeah, so the widths are not taken into account, but one can do that with like Bright-Wigner modeling and things like that. But in this case, the widths are all taken to be just delta functions basically. Yeah, but that's another direction that one can incorporate on top of something like this and see it possibly even better improvement. Yeah. Yes.
Can you go to the previous one?
Yeah.
Or I guess there's this one.
Yeah.
So basically the difference between the black curve and the red dash is the different lists that you need.
Exactly. Yeah.
Okay.
Yeah. So you can think of it like, if I can just go back for a second, bear with me. If you just think of it as I have less pressure when I have fewer states to sum over, that's essentially all it is. So I have a larger pressure when I have more states. Does that make sense?
Okay, so it's not like more exotic states will contribute less to the partition function, or
more exotic states will be suppressed by their heavier mass. That's true. But if you have, so that's another thing, that these lists have a cutoff in mass of about 2.5 GeV. So you're really just hitting like strange states. You're not hitting anything too exotic here. Okay. Does that make sense?
yeah.
It's really about this number over which you sum.
So in the end, there's still a large difference between different lists that you use, just because I guess there are so many more like strange states in the one model. Than
Exactly. You see this high density over here compared to lower the lists at the other two lists.
Okay. But like, I guess when you want to compare with lattice, which one is like the best to compare with?
Yeah, so there was a previous analysis actually where this plot come from, this analysis here, that broke down the partial pressures from Lattice QCD. So basically you can look at the different sectors. So you can look at just a meson gas. So a meson gas with no strangeness. We have just a pion. We can look at baryon number and strangeness equal to 1. So, you know, something like lambda, so, and it's, you know, higher order resonances, and figure out, compared to the HRG model calculations, what states are actually, you know, being probed in there. And from that analysis, this 2016 plus list was actually the one that found to agree. That was found to agree the best. Yeah, but I'm going to show in this talk that we find a similar conclusion by looking at different susceptibilities as well. So again, that was looking at partial pressures, and in each of the sectors, the 2016 plus list is the best.
And then I guess another question is it true that like lattice only applies to small UV? Or...
Yes, so right. So when you have you know, the lattice calculations, they're only done at either imaginary or vanishing chemical potential, and then you probably use a Taylor expansion or do some analytic continuation to get the finite chemical potential, so that will have increased error bars as you go larger in UV.
So the region that you compare HRG with lattice is only for the small UV and
it's actually going to be at UV equals 0.
oh, okay.
Yes. So I'm going to compare directly to the lattice data. So I'm only going to have lattice data at UV equals 0. Yeah, good questions. Anyone else? Okay, let's keep going. All right. Yeah, okay, so I was defining the model. So basically, the hardcore radius that is being incorporated that is going to give this repulsion between baryons or antibaryons is going to be a term that looks like this. So I'm going to have the baryon excluded volume pressure with some hardcore radius, which is the B term, this extra parameter, this free parameter that I'm introducing. And when I do so, now I have some transcendental function, but I'm really lucky because Mathematica knows about this. So I can just get access to this nice solution analytically in Mathematica. Easy peasy. Okay, so if we first want to constrain this new free parameter that we added, this hardcore radius B, we can look at all three of these different lists, UG 2016, 2016 and fourth model, and we see that for these different ratios of fourth order moments, so I have phi 4 over chi 2b, but I also have here mixed susceptibilities, so the fourth to second order baryon strangeness and the fourth to second order baryon charge. And if I just look at the different colors here, shown by these different bands, they're all pretty much on top of each other. So this tells me that it's not very sensitive to the hadronic spectrum, and I can use this to try to constrain my excluded volume parameter. So if I want to look at what do I have in terms of my constraints on that new free parameter, then I can look at the agreement with the Lattice QCD data. So these bands are for a range of this excluded volume parameter between 0.4 and 1, where 1 is the maximum. And I'm just reminding you that if you have the ideal HRG model, then you have no hardcore radius, so that's equal 0. And that's the farthest away from equals 1, way down here. And if we use, you know, something like 0.4 for me, then we have a good description of the, let's say, lower temperature states. And as you move down, this temperature dependence of the pressure starts to become more relevant, and you see this band kind of shape. So it's really interesting. I showed that I'm looking at several different lattice data in this plot. And in this model, we actually have a nice thing where all of these three ratios are predicted to be exactly the same. So we can figure out where the model breaks down when the data, which is supposed to agree from the lattice, actually starts to deviate. So the model breaks down when we have no more agreement between lattice and QCD, but it kind of also makes sense that it would be somewhere in this range where you don't have hadrons anymore, right? We have a deconfined medium. So we have consistency check there for this. Okay, so we have a constraint on B between 0.4 and 1. That's great. Now let's look at the hadronic spectrum. So if we take these second order ratios, so mixed susceptibility over the diagonal one for baryon number for electric charge and strangeness, then we can see again what best agrees, what list best agrees with the lattice data for those results. The lattice data are here in black, and again these different curves are the different lists. And what you can see is there's no dependence, there's no band anymore, right? So the B parameter drops out exactly when I have these types of ratios. So I'm just taking these derivatives, and all that I get down when I take those derivatives are the different constructions. So that's very nice. I can look at these ratios, and I only have a sensitivity to the particle spectrum. So what's pretty obvious is that the vanilla case is not going to describe this data very well, right? So there's definitely a need for more strange states. Whether or not the PDG 2016 or the Quark model list is better is not clear yet. That's not clear from these because of the error bars maybe on the last QCD results.
I have a small question.
Yeah.
On the right, so I mean, I understand the purpose of taking the ratio those to cancel out the volume.
Yeah.
But in this case, you have the baryon and the stream susceptibilities over just the baryon, right?
Right.
And I don't think that, okay, this isn't like from my side, I don't think that the volumes are necessarily going to be the same all the time.
Mhm.
So is there any way that you can actually, I don't know, get some type of like volume dependence out without making the assumption that the volumes are the same?
So this is something that is possible to do within the model to give different eigenvolumes to the different off-diagonal elements as well. So you could say if I have a strained baryon, it has this size, or
Right.
if I have, a non-strained baryon, it has a different size. But it's more complicated.
Sure.
But it's something that we're interested in pursuing in the future. It's a very good point. So yeah, nothing tells me that the volume
Right.
of the strange particle has to be the same, but that's what we're assuming in this very simplistic, minimalistic extension of the ideal nature.
Okay.
Yeah, but it's something that we can explore.
Cool.
It just takes a little more.
Sure.
Yeah, a little more breaking open the model. Okay. So let's look at those strange susceptibilities and see if we can kind of get a feel for getting more information about which hadronic spectrum actually is the right one, whether it's again 2016 plus or the Quark model. So I have higher order strange susceptibilities, and again this Quark mixed susceptibility. And you can see for these, the error bars on a lot of data are relatively large, although there are many points, so many as function of temperature. And let's load this one up just to show, okay, what are the different bands here? So the one which is the smallest excluded volume is going to be the one on top, and one which is the largest is the one which has which is on the bottom with this nice curvature here. So what you can see is when I compare it to the lattice data with this red Quark model curve, I can only get agreement in this transition region at the very bottom of the band. So I only have agreement for this particular list when I have a large hardcore radius. And the opposite is true for a 2016 plus list. So I have better agreement. I'm not just on the edge of the band here. I actually have a little bit more of let's say wiggle room in the error bars here. But what we see is something that's kind of obvious actually if you think about it. So if you have more states, you have more attractive interaction. If you have a larger radius, you have more repulsive interaction. This is something natural that one could expect. But if we had better Lattice QCD data with better error bars, we could kind of discriminate this picture a little bit better and see which list fits best. So we have kind of two different scenarios. We have two lists that both look good, the 2016 plus and the Quark model. But with the caveat that, as I mentioned when I first introduced it, the Quark model is like a limiting case, right? This is the most states that we could possibly use. So there are many, many more than the PDG would aspire to measure. And so we have these two scenarios. If we have Quark model limiting case scenario, we need a large excluded volume. If we have the 2016 plus scenario, then we need a smaller excluded volume, which, yeah, if we also think about the and I think I was explaining to Yoshi before, then the 2016 plus list agreed better with the partial pressures, so maybe that's the one that we can kind of move forward with as the best case. Okay, quick question,
Yes.
because
So using what the quark model has more states than we could aspire to measure. I mean, in principle, somebody could sit and stamp collect away, right? But I thought at some point the quark model gets that the resonances are so broad that like, one, you almost can't measure it because they're basically overlapping states of such broad.
Yeah.
So it's not so much that, let's say somebody could, if they were all delta functions, you could send people
Right,
to measure them.
right.
They become almost non-state.
No, I agree with you. I agree with you. I think it was a matter of more choice of words on my side. Yeah, it's really that they're not possible to measure. No worries. Okay, so that concludes this part, and I hope I could address your question in the beginning about interactions and the model and how we can get some agreement there when adding interactions. So let's go now to a different flavor, which is looking at different correlators of conserved charges. And this is something really interesting because different particles carry different conserved charges, and so you can think about these fluctuations. Then, if I just look at kind of the diagonal here, then I'm probing only the single conserved charge that I'm looking at here. But if I look at all these off diagonals, then I consider cross-correlators between these different conserved charges. And if I am very keen, I can try to figure out which hadronic species are actually contributing to each of these cross-correlators, because the different species carry different conserved charges. So for example, a cation is going to carry both charge and strangeness, while an omega is going to carry everything that I can throw at it, basically. So Starr came up with these measurements for different cross or particle correlations, let's say, that maybe could be considered conserved charge correlators. The question I'm going to ask is, are these both proxies? So, for example, if you have a pion-cation correlator, that might be something like a baryon-strangeness correlator, right? We have, baryon carried by the proton, strangeness carried by the cation. And for a charged proton quantity, we could also look at baryon charge cross-correlators, or for Q and K, we would have a QS cross-correlator essentially. So what we did in this analysis was to, again, compare Lattice QCD data to the Hadron Resonance Gas model. And that allows us to see, okay, what's the full conserved charge correlator that I get from having, the quark symbol on the lattice that's going to tell me about the strongly interacting matter from first principles. And we have different conserved charge correlators. So, for example, a baryon charge, a baryon strangeness, and a charge strangeness. And these would be continuous extrapolated results, again, at nu equals 0. And now we can use the HRG model to figure out what hadrons are actually contributing to each of these correlators here from the lattice. So I should say that chronologically, actually, this study was before the previous one. So this is all ideal HRG model. So just to make sure that we are on the same page with which model is actually going into this. So this is, again, point particles, right? Okay, so for each of those correlators, as measured on the lattice, all the lattice points are shown in pink, and the HRG model curves are shown in the different sequences. So we can compare the total amount of this correlator from the HRG model to the Lattice QCD data to make sure HRG model still works. We still can describe Lattice QCD data with HRG model, which is shown by the agreement with the pink and the black curve and the pink dots. And then we can break down which species are measurable versus not measurable and try to capture what hadrons are actually contributing to these cross-correlators. So our cross-correlators are constructed as all net particle quantities. This is going to be, for example, for the net baryon, we'll have particle minus antiparticle for each of these states. So what we have here are the definition of the measurable quantities. So these are, in principle, the ones which are most typically measured from the experiment: the pions, cation, protons, and the size areas. And from the comparison between the measurable part, which in this case for a baryon strangeness correlator is split about 50-50, because many are not measurable, including those which are neutral, for example. We can then go in and look at specific particle correlators to figure out which hadrons are contributing to it. So let's keep digging into this baryon strange correlator because I'm particularly interested in that one, for example. So if we look at the measured contribution, which is this blue curve here, you'll see that the one which describes the most is actually self-correlations between the lambdas, and the other strange species contribute a bit less. But here, my pointer just went out, so that's fine. I'll just use my mouse. Yeah. So the proton kanon correlator, for example, is a negligible contribution. So you can see down here, the purple one, which is, on this scale, almost zero. And yeah, if we look at the not measured one, you can see everything pretty much contributes equally there. Now, if we look at the diagonal strangeness quantity, then we can break down also what contributes there. And to the measured one, it's mostly kanon self-correlations. So we have that the kanon is actually a good proxy for strangeness, which is great from a particle production standpoint because that's the most strange particles I'm going to produce, and it carries most of the observed charges. So I really like ratios because I can cancel all the volume dependence. So let's try to create a proxy from the theoretical side that can actually be something that the experiment can go after. And this is going to be the baryon strangeness proxy that we construct with the baryon strangeness correlator in the top and the strangeness in the bottom. And so if we look at all the different combinations that are possible of this proxy, then we can see which one best agrees with the total amount of this cross-correlator. And if we just look at the leading contributions from the numerator denominator, then that would be the lambda variance over the kanon variance. But that one in the transition region overshoots. And since the transition region is something that we're particularly interested in describing in chemical freeze-out area, this is not going to be the quantity that we want to achieve. So maybe we should add something to the denominator to kind of bring that down. And so if we add the kanon variance in the denominator as well, the lambda variance in the denominator as well, then we get this blue curve, which agrees pretty well with the black curve. And then if we add, for example, all possible strange states that are measured, again, this one kind of overshoots. So the best choice is going to be this sum of the lambda and kanons in the denominator. And just as a consistency check, we see that a correlator between protons and kanons essentially. So that's not going to be a robust proxy. So if we apply if we want to see how this quantity behaves in the QCD phase diagram in order to be able to try to compare it to experimental data, then we can apply the same cuts to our HRG model as those in the experiment and calculate them along parameterized freeze-out curves in the QCD phase diagram. And for example, if we take two different parameterized freeze-out curves, one at T naught, so the initial crossover phase transition temperature of 145 MeV, that would be this blue dotted line here, or an initial one of 165. So again, it's kind of the upper and the lower bands of the transition line. We see that this proxy that was constructed from star data, which was already measured, agrees better with a higher freeze-out temperature, which is indicating that there's some interesting flavor dependence at freeze-out. Maybe that the strange particles require a higher temperature. Okay, so I want to go on to the next one. I have 15 minutes, including questions. So I'm going to kind of go through this quickly and hope that we can discuss in the question section. Okay, so this is a similar slide that I showed in the beginning, looking for critical, nature in the phase diagram means that we need to know what observables to go after. And so these are the higher order moments. And the reason that we want to go for the higher order moments is actually that the correlation length diverges at the critical point. And the higher you take the susceptibilities, the higher it goes with with higher powers of the correlation length. And again, these are the susceptibilities, which are just the pressure with respect to different chemical potentials. Here, the baryon chemical potential. and can be related to the experimental moments if we take these mass ratios. Okay, so how are we going to be able to say anything about the critical point if we don't know where it is and if we don't have something that carries some critical features? We can incorporate a critical point into the QCD phase diagram by using what's known from universality classes. So if there's a critical point in the QCD phase diagram, then it is in the 3D Easy model universality class, and we can basically construct an effective equation of state where we use what we know from Lattice QCD where it's available, i.e. U equals 0, and add critical features from this universality class in the 3D Easy model somewhere in the phase diagram, and we essentially just paste the critical phase diagram onto the one from QCD via a mapping that looks like this. So we have several free parameters in that mapping, so we can go down from 6 free parameters, which essentially are the location of the critical point. So you choose to put it somewhere, and this does not provide a prediction for the critical point. It's really just pasting the 3D Easy model onto the phase diagram. So you can choose the location, you can choose the angles between the QCD phase diagram axes and the easing ones, and you can also choose overall scale factors. So you have, how much the overall easing contribution to the phase diagram takes, which is this one W, or you can decide how much this transition line by itself, so that's going to be in the easing model, the R axis contributes to the phase diagram. So if we say our critical point is going to lie along the chiral phase transition line, we can go from 6 to 4. Because we have this relationship between the choice of the new VC that has the relationship between the curvature that's known from Lattice QCD as the chiral phase transition line curvature. We get this constraint on the angle, and if we know UVC, then we know TC from the chiral phase transition line. Yes.
Forgive me, but what about the motivation from the 3D Island model here?
Yeah, so it's really from the standpoint that if we could measure something like critical exponents in the QCD phase diagram, they would be the same ones as that from the 3D Easing model. So it's universality classes, and how this has been shown, since we can't actually get a block of QGP and try to measure what happens when it goes to its critical point. So this has been done from renormalization group. So you can basically see how the renormalization group flows to the different critical exponents and extract them in its 3D Easing model. Sure. Okay, so we can study how strong a critical point will be in the QCD phase diagram by looking at different choices of these different scaling parameters in our effective equation of state, which from now on is, I think, known as the best equation of state from this unity scan theory collaboration that was previously funded. Now the funding period is over. So what I'm showing here are varying the parameters for that scaling W and rho across this kind of, I guess, subplots. And if we look at just one for a moment, we have the largest signal, so the largest value of the kurtosis from the smallest contribution of these, from the smallest scaling parameters that we have here. So again, just getting a better look here. So if we have very black regions, this is large and negative, and the white regions are large and positive, and the gray areas are just close to 1. And what's also shown on here are trajectories through the phase diagram, which are given by essentially an ideal trajectory where you would have an isentrope, which is constant entropy per baryon number. So if you think of like an isotherm, which has constant temperature, and this is constant entropy per baryon number, which is the case if you have something which is a perfect fluid. So if you have no viscosity, in the absence of viscosity, you would have these isotherms which show you the trajectories through the phase diagram. So what's really interesting is that near a critical point, you have this lensing effect. So you have a stronger concentration of isotopes as you approach the critical point, and this is something that we can also see changing as we change the equation state. Yes. So if we look now at all the different choices of these configurations of the equation of state, if you see the kurtosis is kind of stretched along T for this choice of small mapping parameters, or stretched along UV, you have a weaker signal when it's stretched along UV, and a stronger signal when it's stretched along T for both the kurtosis and the Lorentz. So in order to estimate what's going on out of equilibrium, because when you approach critical point, things aren't going to stay in equilibrium because you have critical slowing down. So it's very hard to get the system back in equilibrium. So estimating off equilibrium will be important for being able to say anything about what those features might look like from an experimental perspective. So if we look at, for example, what the kurtosis looks like extracted from different freeze-out points. So if we have the freeze-out temperature 1 MeV away from the transition line, 3 MeV from the transition line, or 5 MeV from the transition line, we see different signals here. So I'm going to select this one because this is the equation of state choice that we looked at before, which gives us the strongest critical point. So again, if we have different choices of the freeze-out window, we have a very strong signal when we're very close to the transition line, we're very close to the critical point, and that gets weaker as we go farther away. We have a freeze-out temperature that's farther away from the critical line. And if we compare now equilibrium and off equilibrium results, we can see, what's the true effect that might be able to be seen in the phase diagram, and that's what I'm showing here. So the average chi4 are the points here that have been extracted from the previous plot that I showed for the hydrodynamic simulations, and the x's are the isentropic trajectories at the same freeze-out temperatures corresponding to the different off equilibrium results next to them. And this is for different equations of state. So again, the largest value that's going to be extracted for the kurtosis is for this smallest values of parameter for the equation of state. And we can see that there's an effect on the choice of the equation of state, but also where the freeze-out temperature sits in the phase diagram. So with that, I will quickly wrap up and hope for questions. So in the first part, we looked at the HRG model. We looked at what happens when we add interactions, and we constrain the free parameters from the hadronic spectrum side and from adding this hardcore radius side. And we found if we have many states in the quark model, we need a larger excluded volume. And if we have something like the 2016 plus list, we need a smaller excluded volume. In the correlated conserved charges, we saw that the baryon strangeness property is actually mostly made up of self-particle correlations, so the variances of the mechanical lambdas. And for the critical point, we've seen that it matters what the size and shape of the critical region is as to how strong your signal will be. So with that, thank you.
Thank you, Jamie, for your great talk. So we have some time for questions. I'm going to open the floor first to people on the outside. I know there's a few people zooming in. Does anybody have any questions? I guess you can raise your hand.
Yeah, sure. Can I just speak out?
Yeah, hold up. Give me a second. Let me just raise the volume. Go ahead, Tom.
Oh yeah, sure. Yeah. Thanks, Jamie, for the great talk. So I have a question when you are talking about like the baryon strangeness correlators. So when you talk about like the self-correlators, I noticed there are like one. Yes, right here. So on the orange line, like otherwise they're just like one correlator with one particle with the other, the correlator. But there's the orange line. There's like 4 times the self-correlator of lambda and 9 times the self-correlator of omega. So can you just explain more about like where these parameters coming from and why basically you're like putting them together as like one line instead of just separating them out? And also, since we're talking, okay, so, and maybe like the sigma plus self-correlator and sigma minus, they probably make more sense, but like, yeah, basically why they are combined as well. Mm-hmm.
Yeah, okay, so in particular, let me go for the coefficients in front first. So essentially, the reason that it's 4 times xi is because you have 2 strange quarks inside the xi. so they contribute more, right? They have more strange parts, so they contribute more. And this thing goes for the omega, 3 strange particles. And the reason it's combined here together, I mean, we could have plotted them separately, sure, but contribute enough to merit separating them. So we just say, okay, let's look at what the rest of the strange particles that can be measured will contribute. And so it's just a choice.
Okay, gotcha. And the other thing I guess is like more general is that like I understand basically when you want to calculate the correlator between one particle and the other, then you can look like event by event. But can you explain more about how do you calculate the self-correlator, like just from a calculational point of view, how you achieve that?
Self-correlate between like hadronic species, you mean? So for example, a proton like self-correlator.
Yes. So basically the K0 K0 self-correlator, just take that for an example where like whatever is self-correlator.
Yeah, so within the HRG model, it's really nice to calculate these correlators. So if I had, instead of showing here an orthogonal one, if I wanted to look at specifically some hadronic species, then I would just have a very similar setup where all I need to do is calculate these susceptibility that contribute at that order. So for example, for kaons, a kaon correlator, I would have 2 derivatives with respect to strangeness here, and then I can extract how much the kaon will actually contribute by considering its branching ratios. That's what I'm explicitly showing here. So basically, instead of having 2 separate quantities, I would just have the branching ratio contributions from the kaon squared.
Okay, thanks.
Thanks, Tom. Anybody in the room, any extra questions that they know and ask Jamie? I mean, I'm curious about expanding the PDG list, because I mean, the result, and you were talking about this earlier, but I'm curious about like, from the moment the 2016 plus list was produced till now, there has clearly been some states that have been found.
Yeah.
And from what I found out today was that they don't quite match the states that we estimated for the 2016 plus list.
Yeah.
So I was wondering, like, what sort of effect will they have on these results, and if any, is it negligible?
Yeah, so there is work being done in collaboration with people at UIUC in Illinois, and they're coming up with the updated version, which is going to be PG 2021 plus. And that list is taking into account all these new states that have been found, and also updating any branching ratios that had to be kind of modeled here because we didn't know them at the time. Yeah, so from a thermodynamic standpoint, we're not seeing any difference between 2016 and 2020 plus. So that list basically already exists, and I've looked into, for example, if I wanted to calculate susceptibilities, there's not much of a difference. If I look at the partial pressures, there is a difference because there was an extra megabaryon that was measured more recently. So if you look into the fine details of the hadronic spectrum, you'll see some differences. So for example, this higher order strangeness might be a little bit larger because I have that extra change state here, but it will lie somewhere in between the Quark model and the 2016 pluses for sure.
Because I guess the 16 plus, I mean, we tend to think that that's like the sweet spot, right, between too few states. So I was just wondering, like, if that statement, is still valid, because it's, I mean, I say that all the time, and like, I just wanted to make sure that like these quantities kind of within areas are still kind of the same.
Yeah.
Cool. Anybody else? All right, if that's it, then let's take Jamie one last time.